In this chapter, we have already introduced two of the components or two of the questions that we were trying to address. The first one was what, the second one is how, and the third one is why. So to speak, the first one, what is hotness, what we experience in the world. And we defined that as temperature and came up with some mathematical ways and experimental ways of actually defining it. And then we introduced a microscopic definition that comes from the kinetic theory of gases, which was the idea that the temperature is just a measurement or it's just a macroscopic description of the microscopic average kinetic energy of the particles. Then we went to say, well, how does this work, how things become hot, and we saw that's the transfer of heat, and the heat is actually equivalent to mechanical work, and so we have the heat mechanical work equivalence, and then we can generalize the conservation law with the first law of thermodynamics, which is the change in energy is going to be given by the work plus the heat. And finally, we go to the point that says, okay, we have been observing all along, we've taken for granted, in fact, because that's something that we always observe, that temperature flows from the hot side into the cold side, such as if I have water at 100 Celsius, or let's say 80 Celsius and water at 20 Celsius, and I put them both together, I'm going to reach an equilibrium temperature. Again, equilibrium temperature coming from Zeno's principle of, or Zeno's law of thermodynamics, and it's going to be an equilibrium temperature, which is going to be halfway, or it depends on the masses anyways, but it's going to be in between the 20 and 80 Celsius, right? So that means that the hot water cools down and the cool one heats up. And so the thing here is that we never observed that if I put 20 and 80 Celsius water together, I never observed that I end up having, let's say, two amounts of water, one at 10 degrees and the other one at 90 or something like that, right? So we don't observe that the hot things become hotter in contact with cool ones, and we don't observe that cool things become cooler in contact with hot ones. We always observe that the heat flows from high temperature to low temperature. Why is this? We're going to see towards the end. Basically, this is the idea of the second law of thermodynamics, which is the idea described by this magnitude that we call entropy. Now, historically, we have introduced this idea from engines, heat engines, and in fact, we're going to be seeing today heat engines and applications of those, and connected them to this idea of work. So probably it just makes sense to start with describing engines, and then describe and then make, let's say, an overview of the interpretations that we can make of the second law of thermodynamics. Because one of the interesting things of second law of thermodynamics is that you can find many different enunciations or statements that describe them, and it's very interesting that all of those are actually equivalent. We will not show how those are equivalent, but they just are equivalent because they point to exactly the same phenomena, which is the underlying reason why we observe the heat flows from hot to cold in natural reversible process, right? We're going to do this a lot without a lot of notation that it's typically used when you're going to study thermodynamics more seriously. The reason, of course, is that we are more interested only in the concepts, to understand the foundations upon which we can then build advanced knowledge. And so we're going to relax a lot of the terminology, and only if you go for a deeper study of thermodynamics, whether from chemistry perspective or from physics perspective, then there's going to be time for you to actually be more precise in understanding what do we mean by reversible process in thermodynamics and what is rigorously defined as a reversible process. Because we understand a reversible thing is something that you can just reverse, but it's not exactly the sense in which it's used in thermodynamics. It's something much more precise. So all those things, we're going to leave them aside. So if you actually know thermodynamics, this might be to use something like dumbed down, and it's actually so, but this is because we're interested in the principles. Okay, so with this warning out of the way, we can just directly jump into this idea of heat engines. So we left it in the chapter, in the previous video, with the idea of heat, with this experiment of Count Ramford and James Prescott Joule. And Joule observed this thing where, Count Ramford observed this thing when boring cannon underwater allowed him to boil water, and there was therefore this could be taken on forever, this could be used forever. And he said, okay, then it cannot be a liquid, it cannot be a fluid, heat cannot be a fluid that goes from the boring tool to the canyon, right? Because I can produce an indefinite amount of this, and so it cannot be a material thing, right? And so we just disregard completely this idea of caloric, upon which many of the things, even the word itself, calorie, comes from, right? And from that, we're going to go to the second experiment, which is Joule's experiment. Joule is very interested. He's a brewer, and he is interested in actually observing how we can improve the performance of some engines. Most of or many of the concepts in thermodynamics are going to be developed precisely incentivized by this idea of developing engines and how to produce more efficient engines. A case in point, a beautiful case in point is precisely this one, this entire section, let's say, on entropy, right? As we will see with a Carnot ideal cycle, etc. So this is going to be the first thing. Eventually we're going to reach an understanding of entropy, as in all the previous cases, that comes from the microscopic nature. And so we're going to circle back, so to speak. We're going to just close the loop and finally say that there is a coherent understanding of nature from this perspective. So the first thing we're going to say is that we know there is a heat equivalent, there's a mechanical equivalent of heat, and then we can see that very simply. Can't run for these heat experiments, also Joule, but we'll just want to make something even more simpler, right? So let's say that I have here some vein or something with vat or something with water, and then this is open, and it goes like this, and here there is a turbine. This is a turbine that is supposed to rotate, right? This is a turbine, and this is some water, let's say, for the sake of it, let's say water, and then let's put a fire in here. Right? So what we're going to observe is as temperature warms up, there's going to be some vapor, and the vapor is going to leave because it's going to increase, let's say, pressure, so to speak. We could and open and close that valve, depending, right? And so we're going to observe this air is going to flow, it's going to push the wheel, it's going to rotate it, therefore it's going to be mechanical work. So here we add heat, specific heat is going to account for raising the temperature to boiling point, and then extra heat is going to be latent heat to break those bonds, as we saw in the previous video. That's going to generate the vapor is going to flow, it's going to rotate this turbine, and then it's going to produce mechanical work. So out of this we're going to extract mechanical work, maybe to do something, right? And then this is going to go, and we can just leave it here, and then this is, let's say, an exhaust. So air is going to exhaust. So this is going to just leave through here. This is the basic idea. Now, if you try to model this heat engine, this is just basically a heat engine, you can observe that everything boils down precisely to the same thing. We can describe the entire thing as observing what are the critical components for this heat engine or any other heat engine for that matter. We're not interested in the technicalities again. We're not interested much on the engineering aspect with a lot of precision. We could put another valve here if you wish. And you could analyze instead of with water in a heat engine like this engine, maybe we could think about gasoline engines or many other engines. All of them anyways are going to be described, and this is a beautiful thing by an equivalent thing. An equivalent thing is that you're going to have some hot side at a certain temperature T sub H. You're going to have a system here. This is going to be extracting work, right? And you're going to have a cold side at a temperature T sub C, let's call it. And every heat engine works the same way. The hot side is delivering or transferring heat into your engine, so to speak, and then the engine produces some work, and then you have some of the heat going out into the cold side. In this particular scenario, the cold side is atmosphere, and many times you don't see the cold side, the cold reservoir, because that's simply atmosphere. In your car, the exhaust is the cold reservoir, so it's taking the gas out into the atmosphere. So this TC is going to be the temperature of the atmosphere, right? And then the TH, the temperature inside the piston when you make the ignition. Okay, so the idea here is going to be that there is some heat being extracted from the hot side. From that heat, we can extract some work that we're going to be using for something, and that is going to have some leftover, let's say, which is going to go to the cold side. Now, this is the basic idea of every heat engine. Again, electrical engines work differently, and in fact, they're not limited by the thermodynamical limits that we're going to see now. But this is the basic idea. Any engine, anything, this is very simple because then we can much more easily see this analogy, right? We're putting heat, let's say, we're putting heat into our engine, extracting work, and then exhausting into the atmosphere. So let's say this is our engine, right? So we're putting heat in, extracting some work, and then we have the exhaust, which is the cold one. Now, this idea of using heat for work is, of course, something that mankind has been very interested from very long time, right? So originally, man has been forced to work. I mean, that's nature, and we've never been really very kind of actually putting effort in doing things. So we found ideas, machines, tools to simplify our task. And of course, naturally, historically, that was the reason why we started to domesticate animals. So animals can perform the task. But the problem of animals, of course, is that animals are alive, so you have to feed them, they can get sick, they die, you have to train them, so you have to make a large investment, and they're also limited because they're animals, they're just living creatures, right? And so at some point people started to see how can we exchange part of that animal, how can we replace animals for something else? And some ideas that the guys that developed thermodynamics had in mind was precisely like, for instance, by the way, Joule, who actually, without being there, predicted how much will be the increase in temperature of Niagara Falls. as the water falls and hits the ground, right? And the idea here is going to say, okay, we see that sometimes we can do work with wind. So nature pushes us, so we just don't need to row anymore. Or we can use, for instance, water to turn a mill. And so we're using the river flowing to actually extract work. So these are the ideas of machines. But at some point we say, can we somehow, the machine, this water, this air cannot be controlled. So we introduce animals. And so can we somehow replace animals with something else? And this is the idea over here. We can replace animals with heat, and if you use heat, then you're using a heat engine. And again, heat engines, you can find the first ones, I think, that we have recorded in the 1st century after Christ with Hero of Alexandria. He developed a system, that a small sphere with some exhaust, and then he warmed up steam, and the steam will lift, right, and the sphere will rotate. And after that, there's going to be many, many more people researching on how to control heat and try to make some engines that involve heat and use it. Now, the first patent for a heat engine that exists is that one for, and the first machine that was installed and was used precisely in mining. And his inventor, and the guy who awarded the patent, again, is not the first one historically to do these things, right? Thousands of years before, literally, there were first ideas. But the first one actually is from 1600s, early 1600s, and that's Jerónimo Dayan, who is a Spaniard guy who comes up with this device and many other patents. He patented things for ventilation of systems in mining, sort of AC systems. He came up with new furnaces to melt materials in mining. Mining is a very important driving force of all this technological advancement. And he's going to come even with a device, with a design for a submarine. This is 1600s we're talking, 1606 or something like that. And then he's going to come up also with an idea of suit for a diver. And he could bring with the bell and the suit, and the guy could be hours underwater. And this is, again, this is 400 something years ago, so it's amazing. Now, that's not the one known. The one that's more known is that precisely of Thomas Newcomb. He's not the first one actually in Britain. The first one is from 1698, which is Savory. After Savory is going to come Newcomb, which is the first one to be commercialized. And looking into Newcomb's engine, the idea there was just how can we pump water out of the mines and just bring it up. It's one of the ideas that they have, because they're very interested in producing coal to feed these things. But this problem, of course, as you understand, is that you have pressurized gas and very hot. And so if your system is not very reliable and mechanically you have some issues here and there and some defects in fabrication, this is very prone to explode, because you have a large pressure in here that's going to explode. And by the way, that explosion is not just simply problematic because it's explosive, right, mechanically, but also it's at high temperature. So this is a great danger. And so a lot of these innovations and a lot of these big names that we have are precisely from the idea of how can we improve the efficiency, how can we improve the safety of these things. And probably the greatest name of all, of course, is that of Watt, right? And what is going to come with a new system where we redesigns the coal reservoir and puts them, and he increases the efficiency and also the safetiness. And that's why we call unit of power Watt, precisely in his honor. But once being done this historical thing, of course, we stopped using steam engines. Steam engines are very interesting in the story and also thermodynamics, because from a historical point of view, steam engines is the thing that makes possible industrial revolution. Industrial revolution did change the world completely, and also the balance of powers, because industrial revolution at the frontier of that is going to be Britain, and that's going to make Britain to be the hegemonic power in some centuries to come, right? Steam engines are going to be making possible, for instance, the train, and this in America is going to be very important, going from east to west. And steam engines are going to eventually be replaced by, for instance, gasoline and internal combustion engines. That's going to be using gasoline or diesel as most likely your car uses. And so you can think of many different heat engines. Nuclear plants are also a sort of heat engine. Coal plants, oil plants, gas plants, all of those work as heat engines. Nowadays, we're gearing towards electrical engines. There's many reasons for those. One of those is efficiency. Electrical engines are always, depends if you make a very bad engine, no. But typically, electrical engines, well designed, are going to be always more efficient than heat engines. Now, a different question is, of course, where's the energy coming from? Because if the energy is coming eventually from the oil plant, from a gas plant, from a coal plant, then what the heck, right? You're not just getting anything. So this is something to bear in mind. So hopefully when you learn some physics, you're also being able to have a more educated opinion on some of the matters of pressing issues of our time, so to speak. But coming back to the idea of engines, why are engines important? Because this is driving force, and people are going to start thinking, how can I improve the efficiency of these things? Again, hot side delivers some heat, we extract some work, and the leftover just goes there. And here is the thing. With the discussion we had before, according to the first law, we're going to say that the change in energy, of course, is going to be equal to heat plus work. Now, it's important to write this as saying what heat comes into my system. That's going to be, let's say, QH, right? So that's positive. It's heat transferred to the system. This heat is transferred from the system, so that's going to be negative. And finally, this work is extracted from the system, so we need to take it negative, right? It's work done by the system, not work done on the system. So that's going to be giving us the balance of energy. But of course, if energy needs to be conserved, and of course we are assuming this is conserved, that's going to be 0, which is another way of saying that basically what we have is that work, we could say, let's say work, it's equal to QH, of course, minus QC, right? The difference between the heat taken out. And then we can define, what we can say is the efficiency of this engine. How efficient are we? And when you're asking about efficiency, the very important thing to bear in mind is that you have to compare what you have to pay for what you get. What you want to get in an engine is work. That's what you want. What you want from your car is that it takes you places, right? So that's what you want. That's the work that the car is producing. What you have to pay, of course, is the gasoline you put, right? So that's going to be the heat that you input into the system to produce this work. And so when we define efficiency, we can just define it probably over here, right? Efficiency is going to be defined, E for efficiency, or we could use eta or something like that, is going to be defined as what I want divided what I pay. And in this case, what do I want? And this is going to be good for this, but also for refrigeration and heat pumps that we will see in a second later. What is in a second? What is what I want? What I want is work. What is what I have to pay? What I have to pay or what I have to input is QH. And then if you write this thing in terms of that, you have QH minus QC divided by QH. And we can rewrite that thing as simply as the efficiency. Let's write it down here. Let's write it up here, excuse me. Efficiency in there, there's going to be 1 minus QC divided by QH. And this is the definition of efficiency of a heat engine. For any heat engine, this is going to be the efficiency. It's 1 minus the ratio of the cold to the hot side. This is the first idea that we want to discuss for engines. It's going to be very useful in efficiency. It's going to be useful in describing these systems, these engines. And from here, we already can ask the first question. If I'm interested in making something more efficient, what do I have to do? Well, I want to make this to be as small as possible, right? And you do that by bringing QC to 0. In other words, if all the heat I put in goes out, because of course, increasing the heat that you put in, it doesn't really help you much, because the heat in, the balance is going to be there, right? The heat is what you put in, so you can always put more, but that doesn't really, it's not something that you want to do, right? So for a given heat, you want to make sure that there is no heat out, because this is energy, this is energy, this is energy, energy in, energy out. How do you make more efficient? If this is what I want is to make this to be 0. So what I want is that to be 0. And this is the idea they have. Can we somehow make an engine that has 0 heat going to the cold side, right, to the cold reservoir? The answer to that is going to be no. And in fact, there's going to be a French engineer, a very young a man from a family of engineers and military. All of these guys are militaries and engineers. And he's going to come up with an ideal model. We will not get into the details. His name is Sadiq Carnot. And he's going to prove that actually efficiency of an engine is limited. It's actually limited to be 1 minus temperature of the cold side divided by the temperature of the hot side. And we call this the ideal or the Carnot efficiency of any engine, steam or whatever, right? You have to divide the temperature of the cold side by the temperature of the hot side, and that's going to give you the ideal. This means this is the maximum temperature that you can achieve. Now let's erase here and put these two things here and make some analysis on what this means. So this is what we have observed, that for any heat engine, we're going to have an efficiency which is 1 minus the ratio of the cold and to the hot side. But we can come up with an ideal one that comes again from Sadiq Carnot. And Carnot designs an engine which had the best possible efficiency, and he figures out that the maximum efficiency actually is 1 minus the ratio of these temperatures. And so we say, how can we achieve 100% efficiency? Right? How do we achieve that efficiency? Well, there's two routes to achieve 100% efficiency. In this case, efficiency is on unit. If you multiply times 100, then it's going to be percentage. So 1 minus this, how do you make this to be the maximum? Is to make it this 0. How can you achieve that to be 0? Well, of course, the first option is to say that the h, let's say, goes to infinity. If this number goes very large, goes to infinity, this is going to cancel, and it's going to be 0. And the other option is going to be that dc goes to 0. Actually, we could just say equal to 0, right? So 0 kelvins. It's important here, by the way, that you notice this is in Kelvin. We're always working with temperature in Kelvin in this chapter, in these things. We are allowed to use Celsius in calorimetry because we're calculating difference in temperatures. But in here, be extra careful also for expansion of things to use for ideal gas, use absolute pressure and temperature in Kelvin. Or be careful otherwise with the constant. But anyway. So here's the idea, right? So we have the temperature of the hot side going to infinite or the cold side going to 0. If the temperature of the cold side goes to 0, this is trivial. This is 0 divided by something, it's going to be 0. So 1 minus 0 is 0. This idea of the temperature going to 0, we have from the ideas that we have now understand, is this possible or not? Okay? Now, from a practical point of view, having 0 Kelvin seems extraordinarily difficult. So that means that this ideal scenario, which is when we can achieve 100%, it's going to require to have 0 Kelvin, or it's going to require to have infinite temperature. Now, obviously, from practical standpoint, again, just practical, you cannot have an engine with infinite temperature because it's very difficult. How on earth are you going to just warm up something so much and so high that the increase in temperature? Then your metal is going to melt. If you're using iron or you're using aluminum or you're using steel, there's a limit also, which is for sure the melting point of the material itself. So this ideal limit is not really that helpful in any ways, practically speaking, right? Because you cannot really have infinite temperature. But from a principle, from a first principles point of view, this is actually impossible. Why is this impossible? Actually, both of them are impossible, right? So we're going to say that both this is impossible. And again, this is as a matter of principle. And why is this impossible? Well, the temperature is going to infinite. What is temperature? Temperature is related to the average kinetic energy of the particles. If the temperature is infinite, what is the average kinetic energy of the particles infinite? But can anything have infinite energy? No, we know that's not the case, because if it was infinite, again, infinite is not a physical number. Infinite is just a mathematical idea. It's something very, very large. But in physics, things are not very, very large unambiguously. They need to be specifically something. As large as you wish, but will never be infinite, right? So practically we know it's impossible, but also as a matter of principle, you can never reach infinite energy. And you know now why, because that would require to have an infinite amount of energy, and that's stupid, right? So the second problem is, can we do then, okay, maybe we can go to 0 Kelvin. And when we discussed Celsius and Fahrenheit scales, we said, well, these are arbitrary, we were using 2 points, and then we make degrees in between to make the steps in between the temperatures. And those are scales, and that's why we call them degree Fahrenheit or degrees Celsius. But now we have an issue, because then we introduce the idea of Kelvin degrees, which comes and we say this is absolute temperature. Why is it absolute temperature? It's not a scale, it's an absolute number that comes precisely from this. And what is the minimum temperature you can have is 0. And what does this correspond to? To 0 kinetic energy. Now, quantum mechanics says this is actually not the case. Even materials at 0 Kelvin would have some motion. But more importantly, there is what we call the third law of thermodynamics that says that it's impossible. And again, there's many precisions to do here to be rigorous with the language. We're not going to be. We're just interested in the idea. The third law of thermodynamics says that it is impossible to reach 0 Kelvin. The idea is it's impossible to reach 0 Kelvin in a finite amount of steps. Okay? In a finite amount of steps, it's impossible. And because we have a finite amount of time anyways, then it's impossible. So as a matter of principle, you neither can achieve infinite temperature nor 0 temperature. As a matter of principle, again, this is not anymore practicality. And so the limit, ideal limit, as a matter of principle, is always smaller than 1. And this is a very important idea that is going to be then described from the point of view of the second law of thermodynamics. And it's going to tell you it's impossible to make, we could say the second law of thermodynamics is going to tell you it's impossible to make engines to have an ideal efficiency equal to 1. We'll come back to this later, but important thing from the point of view of applications, you can calculate the ideal efficiency of your engine, but in the real case, the real efficiency is given by this thing. And there is a way of saying this is that because we cannot achieve 100%, we're certainly sure that when we go to analyze this, just write it here. The idea that we may have is like saying, oh, how do I make this to be maximum? let's make QC 0. In other words, let's make waste 0, because this, I put this energy and I waste this much energy because this is thrown away, and I say, why I'm throwing this? Let's make this minimum to the point it goes 0, so all the energy comes in, goes to work, which is what I want. Well, that's the second law of thermodynamics is going to tell you it's impossible to have an engine without heat being transferred into the cold reservoir. We'll see this in a second, but this is the first idea for heat engines. Let's see the idea for refrigeration and heat pumps. So the idea here is that we see heat flows from the hot to the cold side, and if we put something in between, we can extract some work. That's the idea of a heat engine. This we call heat engine. Now, one question that we may ask ourselves is, okay, can we do the reverse? Can we take heat from the cold side and transfer it to the hot side? Now, why would this be something that you want to do? Let me put your situation first. Let's say that you're in winter. Let's say that you're in summer. Let's pretend this is Florida in your house. And you're inside here, and here's the sun. And of course the sun radiates into your house, and so it's getting very hot inside. And you say, super hot in here, I would wish this was colder. Now, what you're trying to do now is, of course, you can say that if your house, and this is common sense, if your house was at a higher temperature than the outside, right, then you would open the window, because the air from the outside would come in, and the temperature in your house will become in equilibrium with the outside. So if your house was hotter, you would open the window. Trivial, I mean, that's obvious, right? Now, typically what happens, however, is your house is colder than the outside, right? Of course, Tc being smaller than Th, but it's not cold enough. And so what do you use? You use an AC system. And so your AC system, what it's doing is making your house colder. How do you do that? Oh, I put cool in. That doesn't exist, right? No, that doesn't exist. What we can do is transfer heat. And what's the heat that we want to transfer? We want to transfer heat from our house to the outside. So actually what we want to do is just this. But this is the cold side, and this is the hot side. So what we're doing actually is going from cold to hot. So this is something that we certainly want to do. So what do we need to do to actually achieve this? Well, we need to do work. We need to use the AC system. The AC system you plug to the outlet and it's doing some work. So this is the idea of a refrigeration system. It's just the inverse of a heat engine. So now our system is going to be basically, we're going to define, we have a hot side and we have a cold side, and now what's going to happen is that the cold is going to flow, work is going to be added into, and so we're going to have heat going out. This is the idea for refrigeration. Right, refrigeration. So heat comes from the cold side, and see that the arrow has inverted because now we are reversing the cycle. Because from the outside, from the cold side into the hot side, and now we can just make we'll make conservation of energy in a second. Let me just write another option, which is what we call a heat pump. Let's write the same thing here. Now, heat pump is basically the same. It's an inverted cycle, but in this case, this is the scenario. Let's say that we're in our house, and it is winter. So it's no cloud. I don't know how to make this. It's winter, yeah? And you're inside here, and of course, in winter, typically your house has a hotter temperature than the environment. But maybe it's not. Why? Because of course, if your house was colder, and sometimes it happens that your house is colder than the outside, and it's just better to be outside, so you just open the window. But if your house is hotter than the outside, it might not be hot enough for you, so you don't feel comfortable, so you turn on heating. And so how you achieve that is just by means of a heat pump. Now, of course, you can use resistive heating, but heat pumps are many times, depending on the context, many times more efficient, and we'll see in a second how we calculate the efficiency of these systems. And what is the idea here? That we want to bring heat, we want to raise the temperature in our house, so we need to bring heat in our house. So we are now in the point of view, again, from our house, but in this case, we're going to bring heat inside. But where are we going to take it from? Well, we're going to take it from the outside. So what we're actually doing is just taking energy or taking heat from the cold side and bringing it to the hot. So this is just basically equivalent, right? The difference is just a matter of perspective. In a refrigeration system, we want to bring heat from the cold into the hot to make it colder. in a pump, we want to bring heat from the cold into the hot to make it hotter. But at the end of the day, we are inverting the cycle. And in both cases, we're going to have, this is a heat pump, right? This is a heat pump. What we're going to have to do is just we're taking heat from the cold side to transfer to the hot side, but this comes at the cost of work. So this is exactly the same idea, but now there's two perspectives. One perspective is we're in the house and we want to get rid of heat. So we're going to transfer heat from the cold to the hot. In a heat pump, we're in the house, we're hot, but we're going to be hotter. So we need to bring heat from the outside to the inside. And these are three systems we can discuss. We have discussed this. Let's see the physics, or let's say the two ideas for this in terms of efficiency in this column over here. So remember, what we're interested in efficiency is what I want and what I pay. So I need to make sure that I need to identify what is what I want. So in the case of refrigeration, what I want is to get heat out of the way, right? So I'm from here, this is me right now, and I just want to transfer heat outside of my house. So what I want actually is just get rid of QC. And to do that, I need to pay a price. What's the price? The work that the heat pump does. And that's what we call the efficiency of a refrigeration system. Instead of calling efficiency, sometimes we call it the COP, which stands for the coefficient of performance. So if you go to your hardware store, and understood as a electronics store, right, and try to buy a refrigeration system, it's going to come with a number associated with it, which is the coefficient of performance. Now here's the thing, QC, it's typically, well, you can calculate the ratio, but QC is going to be larger than W, right? So QH is the sum of QC plus W, right? So we could say that QH is of course going to be QC plus W, right? So we're trying to get as much out, and we have to pay some price. Of course, we want to get as little price as possible. And the lower that this is, the higher the efficiency. It turns out, of course, that these numbers are larger than 1. But basically, the idea here is going to have these numbers are going to be a good heat refrigerator. If you're trying to buy, I think typically 5 to 6 as a ratio is usually good, but we will see that as a practicality anyways. The other option is just to discuss, the other alternative is heat pump, right? And in a heat pump, we're going to make the same, but now what I want is I want to do what? I want to put heat inside my house. So what I'm interested is in QH. And what I have to pay is W, right? And so how much it takes for the environment, we don't really care, because the only thing we're interested in is actually how much I'm outputting from this amount of work. Here is how much I'm outputting from my house. Now I'm here. Now my perspective has swapped. So the efficiency also has changed. And now this is also going to be called the COP. And when it's reasonable to use a heat pump, of course, when the coefficient of performance is larger than 1, again, so that's also going to be, let's say, larger than 1. Otherwise, don't use it, obviously. So it depends on the scenario, but typically it is. So coefficient of performance is also going to be larger than 1. So then don't get confused in terms of a heat engine that is always, theoretically, is more than 1 to these ones, which are always larger than 1, okay? So it's an important distinction to bear in mind. What is the difference in here in any case? It's just the distinction between what is what I want to do. I always do work to achieve that. And how is this possible? The subtlety, again, it just will take us too far away, but just to leave there the idea. What we're doing here mostly is just shuffling, or at least in the case of a heat pump, is just creating entropy. And we'll see this in a second why. And whereas a thermal resistive heating just takes power, and you will see in physics 2 that just generates 100% efficiency, so the entire energy is used to generate heat. In here, I don't need to use that much energy to produce that heat, because what I'm doing is taking heat that already exists, taking entropy, and putting it into my system, right? So, well, in the case, yes, exactly, in this case, yes. So what we want to do is just take something that already exists and transfer. So there's a good idea that might help you to remember this system, or this mechanism, which is the comparison between turning on a resistive heater, which puts energy to create heat, to the comparison of taking heat that already exists and bring it in my system, which requires less work, and that's typically why heat pumps are more efficient than thermal resistors, right, which is the standard resistive heating of a radiator, right, at home or something like that. Well, radiators will also have, but basically, the idea here is what is more easier if you want to go from one point to another. Well, one option is just to build a car and then you go. The other option is just to move the car from a car that already exists. Let's say use a car that already exists, and typically using something that already exists costs less than actually producing something new out of nothing, right? And so that's basically the idea in here, right? For heat pumps. But basically, heat engines go in the natural process. We can extract work from this flow of energy. In the case of refrigeration and heat pumps, these are processes that do not occur in nature, and because of that we have to do work because we're breaking that. Now this, just for completeness, let's go now back. We have all the ideas that we need for heat engines. Let's go back now to study the idea of entropy. We come now to one of the last concepts we're going to discuss in here, which is the second law of thermodynamics, and introducing the idea of entropy. Now there's many different equivalent, and this is very important, they are equivalent statements of the second law of thermodynamics, but all of them are answering that question that we asked at the beginning of the chapter of saying why heat flows from QH to QC. Now we have seen engines, and the discussion of Carnot, although we didn't get into many details, we saw how Carnot was trying to find out the most ideal engine, because if you come and you picture in your mind an engine and you say, okay, what things can I do here to improve the efficiency of my engine, some people are going to say, oh, maybe we have to find a new design, maybe we have to choose different materials, maybe instead of using liquid, maybe we can use water, maybe we can use something else, right? So what different materials we're using, and Carnot realized that at the end of the day, efficiency in an ideal scenario depends only on the ratio of temperatures between the hot and the cold side, or the cold to the hot side, right? So that's the idea that the Carnot had. And thinking about this Lord Kelvin, which is Thomson without the P, Thomson with the P is Count Rumford, but this is Lord Kelvin, right? So Rumford is the one for the boring of the canons, as we were discussing last video. So now we're going to have Lord Kelvin, Count Rumford, Lord Kelvin is going to realize the Carnot idea is actually pointing to something much more fundamental. And it's this idea we discuss, which we can say Kelvin statement, we can call it that way. I'm not going to describe it literally, but just the idea. Kelvin statement is going to be related to the fact that whenever I have a hot side and a cold side, it is impossible to achieve a purely, it's impossible to have an engine that goes simply from hot to work without any cold. This is what Kelvin discovered, right? No process is possible whose sole result, no process, we don't need to write, basically it's on the notes, but no process is possible whose sole result is the complete conversion of heat into work. So this, basically what it's telling us is that this is impossible. Let's erase it. This is impossible. You always need to have some cold heat going to the cold reservoir. This is impossible. This is what Kelvin is telling us. So the idea here is Kelvin is telling us you need to have the flow, the complete flow. It's impossible to have a system which sole output of the heat is just work. You need to always have some price to pay. So Kelvin is telling you you have to pay a price. A price, and that price is QC. It's impossible. Now this statement we're going to show them, but thermodynamics books goes through this. This statement prove you that. There's a second idea, which is Clausius' statement. So Rudolf Clausius was a German physicist, and he realized that he was working on these ideas and these systems, and then he was particularly concerned from the fact that heat, which is the question that we originally said, so why heat goes from QH to QC. Q flows, so actually we shouldn't say, we should have said from hot to cold. From hot to cold, heat always flows naturally, because as we see, we can reverse that, but with work, but with naturally, reversibly, with no artificial means. Let's say heat always flows from hot to cold side. So he's asking why heat flows from TH to TC, right? So this is the question that Clausius is trying to answer. And so in his understanding, he's saying that that's actually the case, but in his work, he's going to come up with a particular magnitude. So you remember, for instance, we were saying Newton was trying to explain why things accelerated. He comes up with force is equal mass times acceleration. Or when we were discussing energy, we talked about Leibniz and the vis viva, and we talked about the cards, and the momentum is mass times velocity. These are arbitrary definitions that they have. Of course, they have some insight in their educated guesses, but these are just arbitrary magnitudes we come up with. So Claus is going to say there is a property of a system that we call the entropy, right? There's a property of a system which is entropy, which is a property of the system in equilibrium, we should say, right? Systems in equilibrium. And that property, if I analyze processes and I calculate what is the change in entropy, what he's going to say is that the change in entropy on an isolated system, it's always larger or equal to 0. And mathematically, and this is why it's so important, he's going to show that that change in entropy, it's equal to the ratio of heat divided by the temperature. And this is the equation for Clausius, which is telling you what is the change in entropy. So we don't know exactly what entropy is absolutely. We know that there is something, we can associate something to that system that we call entropy. And then we observe some time later that there has been a change of heat at a certain temperature, and then we say, oh, the change in entropy is this much. And if you calculate this for every process, all the processes have all the processes for the universe, we'll see this with a little detail on the problems, but for the entire universe, because this is for isolated systems, right? For an isolated system, so let's write somewhere isolated. Well, actually, this is what's isolated, right? So for an isolated system, the increase in entropy is always increasing. There is only one case when entropy is 0, and that's the case of reversible processes. And we could say that reversible processes are those that have entropy equal to 0. But basically, for reversible processes, that's 0. But for all the other processes, reversible processes are the ones that are going to happen naturally, which is basically heat flowing from hot to cold. Why does heat flow from hot to cold? Because if it was flowing from cold to hot, it would be increasing the entropy, and that cannot happen. So this is the second law of thermodynamics from the point of view of entropy. Entropy defined as a property of a system's in equilibrium. So for an isolated system, and you can consider that any system is eventually going to be isolated if you consider the system itself plus its surroundings, as we call the universe, right? So the entire universe, the total entropy is going to be 0. So you can always have systems that reduce entropy, but that's always going to come at the expense of increasing the entropy of the entire universe, such that the sum of the entropy of both system and environment, both together, which make the entire universe, that entropy is always increasing. And there's going to be a third, this is the classical approach, right? And there's going to be a third approach to this problem, which is going to come from the point of view of Boltzmann. We have observed these things macroscopically from the point of view of engines. And by the way, these things are compatible. They're equivalent. They're equivalent definitions. You could find that they are actually connected. But we're interested in one final approach to this problem, which is focusing on entropy. Clausius is talking about the change in entropy. And then it's going to come Ludwig Boltzmann, is going to be thinking, but why on earth, how can we explain this, right? Because so far this is observational. There's nothing in here that says that necessarily this is going to happen, right? This is just, we just observe it to happen the same way that we observe conservation of energy. And whenever we see that energy is not being conserved, then we come up with a new source of energy that we didn't account, and then conservation of energy is still conserved. Because there's this fundamental principle say that things need to be conserved. And so now we find that entropy is always increasing in the entire universe, and we're thinking there needs to be something here fundamental. And Boltzmann is trying to find a reason for that, and he is, as we said, the father of statistical mechanics together with Maxwell, and he's going to be working in this problem, and he's going to say, oh, well, Boltzmann is telling you, Clausius is telling you the difference in temperature. What Boltzmann is going to say is that entropy, Boltzmann, there's nothing here. Boltzmann is going to come up with a mathematical definition of entropy. And that's going to be absolute entropy is going to be given by, well, I think this actually comes from Planck, but the idea, the works are in there, right? Which is logarithmic, which is not the natural logarithm, it's the natural logarithm, it's not the base 10, right? So it's not, it's this. That's what we call the, sorry, that's what we say. Ln is just basically logarithm with the Neperian number on the, as the base, okay? So it's not log 10, it's log e. Okay, and this is the amount that he finds. And what is this? Well, Kb is Boltzmann constant. and then omega is the number of microstates for a given macro state. And from this perspective is from the one that we're going to be saying that entropy is disorder. And so we can enunciate the second law of thermodynamics by saying that systems naturally tend to disorder. So systems tend to disorder. And why do they go to disorder? Because of this. And we're going to understand this. We're going to erase this and put it back here to try to make an approach, and we'll have a particular example in the problems addressing this idea. The number of microstates is the number of different options to configure. Remember that this is statistical, so you need an ensemble of particles. So let's say you have 100 particles and you need to be 50 doing whatever. Well, you can get in many different combinations 50 out of those 100 and associate to those 50 that particular thing. So each one of those different ways in which you can associate those particles to do that is going to be a microstate. But the entire system is defined as an entire picture of the whole. That's what we call the macro state, right? So that macro state, it can be made of many different ways. So let's say, for instance, you wanted to make a tower of Lego blocks or something, right? And you say, okay, I need to have 10 blocks. How can I arrange my 10 blocks? Well, there's many different ways in which you can arrange 10 blocks, but if at the end of the day they all are arranged in the same shape, those are different microstates corresponding to the same macrostate, which is the tower, right? We'll see this in a second now, and with one problem. But this is the statistical interpretation of entropy. Now, we can understand why things tend to disorder. It's just simply because they're much more likely. So entropy is just a measurement of, or it's just determining the probability of finding something. So it's not that there is a reason why we go one way or another. The reason, let's say, is just purely statistical. So it is certainly possible that you could have a system where you put ice and water and then you end up with more ice and boiling water. But the problem is that if you calculate the probability of that, that's going to go to 0. It's pretty much negligible, right? So that's the idea here. Because the numbers are going to be so large, you're going to have so many molecules that it just becomes obvious that's not the case. So these are different and equivalent statements, and all this together build the idea from the macroscopic world, starting from the applications, which motivated most of the development of thermodynamics. Then analyzing a more property, a more mathematical, the first time that someone introduces this idea of why heat flows from hot to cold, that's Clausius, and eventually coming with the microscopic, with the particles interpretation of this through Boltzmann. So let's see finally, we'll see in a problem, this application, let's see some problems of engines efficiency, and finally calculating entropies and a statistical interpretation of entropy. So let's solve some problems about engines and entropy. Let's start with this one about the process that we're talking about. A gas is enclosed in a cylinder fitted with a light frictionless piston and maintained at atmospheric pressure. So maybe let's make a small thing, and this is going to be the piston, and it's supposed to be frictionless, right? And so we're saying that the pressure is atmospheric pressure, so this is atmospheric pressure, or 10 to the 5 pascals in international system. And so we're saying maintain at atmospheric pressure. This is a process at constant pressure, right? When 254 kilocalories of heat is added to the gas, and so we add some heat to the gas, and in fact we add how much? We add 254 kilocalories, so kilocalories. So remember from previous video, when we use calories with big C's in food, that means kilocalories. In physics, we never say calories to mean kilocalories because that seems to be stupid, but not everyone is blessed to be a physicist or no physics. So coming back to the problem, when 254 kilocalories are added to the gas, the volume is observed to increase, and it goes from 12 cubic meters to 16.2 cubic meters, right? There is a change in volume, and it says we want to know what is the work, and we're going to be asked what is the change in internal energy of the gas, okay? So let's calculate the work, okay? So what is work for a gas? Well, work is a force times a displacement. We could see that, but basically we can actually do it first. This is the question you know already, but just to say it again. If we have a gas that's expanding, why is it expanding, right? It's because the gas is heating there's the molecules of gas, and the molecules of gas are hitting the wall, and as a result of that, the wall displaces, right? And it produces a displacement delta X, let's say, right? And so eventually you have a larger volume, right? So this is the result of a force times a displacement. So what's work? Force times displacement. So then, yeah, that's important. Okay, so then we can see what is pressure. Well, pressure is the force divided by an area. So if I describe this, force is pressure times area. So let me rewrite work in terms of pressure times area times delta X, which is pressure times area times delta X. But what is area, which is this area times delta X? That's the volume. So that's the pressure of volume of what? The volume of, this is V sub 0. This entire thing is going to V. This volume over here is V minus V sub 0, which is delta V. So it's going to be pressure delta V. So what is work? Is the pressure increase in volume. So how much is the pressure? Is 10 to the 5 pascals. What's the increase in pressure? Is going to be 16.2, in volume minus 12.3, it's 12 meters. And that's going to be 10 to the 5 times 4.2 cubic meters, which of course is going to be 4.2 10 to the 5 joules. And that is the result of the problem. How much work we need to do? We need to do work to generate the space. Basically, it needs to make work because it's creating a space in the piston to fill itself, right? To create that. So that increase in volume requires work because it's pushing the lid. So we see why, because it's pushing the lid. So this much amount of work. Now the second question, by the way, this is work done by the system, because it's the system, which is the gas, working, making a force on something outside, which is, let's say, the gas of the atmosphere, right? So it's work done by the system. So in our sign criteria, which we're using UPAC, right? We said we use UPAC, right? So because in physics, typically, then the question is written something different, but we're using the UPAC, International something for chemistry, the Chemist Society International. Anyway, so then we're going to say that's the amount of work, and this work is done by the system. So in our physics, we're going to have to say that that actually is a negative work. So we will have to add a negative value somewhere, okay? That's important to say. Well, because this is the work done by the gas, so we're going to be taking it as negative, right? It's work done by, so that's negative. Okay, part B says the change in internal energy of the gas. And so we have to remember that the change in internal energy is going to be given by Q plus W, and that's why it's important now, right? We can, if you want, let's not put the sign, and so we just add it by hand, the same thing that we do, for instance, where we say weight, and we define it as positive, but we just put it in the balance as negative. So because the system is doing work by, so we know that the change in energy needs to be equal to heat added to the system, which is 254 kilocalories, plus work. But let's change 254 kilocalories are added to the system. That's 1,000 calories, so that's going to be 481 joules, right? So we need to multiply 254 times 4,180, and that gives 1 megajoule, let's say 1 10 to the 6 joules, okay? So we are adding 1 megajoule to the system, and the system is doing how much work? 4.2, so we can write here 1 10 to the 6, and the work is going to be plus, but now the work is negative because it's done by the system. So the heat comes in, work goes out, okay? So this heat is going to be positive, but this work from the point of view of the gas is negative. So that needs to be plus minus 4.2 10 to the 5. And if you make this, of course, this is 0.4 10 to the 5, so it's going to be about 0.6 10 to the 6, which is megajoules, right? 0.6 megajoules. So what is the change in temperature? 0.6 megajoules. Now here's the question. we could answer, we could just start to think again, and that's the beauty of learning all these basic concepts. We can start to see things. What do we say is the internal energy? Internal energy is going to be the kinetic energy plus the potential energy of binding. We said that in the previous video, right? So this is the gas, let's take this to be 0. So it needs to be in kinetic energy. So this increase is going to make the particles to be moving much faster. If the particles are moving much faster, what's going to be the result of that? Well, there's an increase in the delta U is larger than 0, which means that there is a delta of kinetic energy that is larger than 0, and kinetic energy is proportional to the temperature, therefore the temperature is going to be increasing, right? So because the temperature is going to be increasing, why? Because we put heat, it does work, but it doesn't do as much work as we put heat in, temperature raises. What is this process? This is a process at constant P, and what we observe is that volume C2. For a given volume and a given temperature, now I increase the volume. What needs to happen to the temperature? It needs to increase. You see, we now see finally these ideas all together, and they make sense. I mean, obviously, otherwise what a waste of time. So this is the Charles law, maybe? Or Gay-Lussac. I think it's Charles. A law, just remember. That's Charles. Gay-Lussac is with pressure. So basically, we add heat, some of that heat is used as work. That's the same idea, right? We're going from hot to cold. Some of that is going to as work. We have some remaining is being absorbed, and then the particles are going to be moving much faster. So all of these things together. So let's see another problem. By the way, systems or processes that happen at constant pressure are called isobaric, in case you find that. We are not interested again in the notation, but it is iso means the same, and bar is atmosphere. You remember we use bar also as measurement of pressure, so it's pressure for Greek, and isobaric means at the same pressure. So isobaric. Let's see a problem that happens at constant volume, and then we can call that isochoric or isovolumetric or isometric, I've heard also. So all those refer to the same thing. We're not interested in the labels, but you probably were going to see the labels later on. So let's see this second problem. Now in discussion problem number 2, we said the pressure in an ideal gas is cut in half slowly while being kept in a container with rigid walls. The critical thing here is rigid walls, because when they tell you there's rigid walls, it means that the volume is constant, because it doesn't change, it's rigid, okay? In the process, so we go from P sub 0 to P equal to P sub 0 divided by 2. It's cut in half. In the process, there's some heat out, which is 465 kilojoules. And the question is how much work was done during this process. And what is the change of internal energy? So the same as before, basically, right? So now we see the problem. Well, what's happening now? Systems that happen at constant volume, and again, this is a label we're not interested, are going to be iso, which means same. And now we're going to say choric, or isometric, or isovolumetric. I think I'll figure about it, but I was used to say isochoric, right? C-H-O-R-I-C. So isochoric, which means constant volume. At constant volume, right? And we change the pressure, we cut pressure in by half. So how can we achieve that? And some work that goes out, right? So first, work. What is the work in here? Again, what is the definition of work? Pressure times change in volume, right? Okay. Why? Because again, remember that's the piston moving up to make room for that. Is there anything making a force times the displacement? Is there anything here displacing? No. Is there anything changing volume? No. So what is the thing that describes isochoric processes? That they have zero work. Easy peasy lemon squeezy. So this idea that, I mean, if you start to use labels a lot, then these things become second nature, and you should say, oh, there's an isochoric processor, blah, this and that, isothermal, adiabatic, this, whatever, right? So these are the labels why they're interesting to introduce labels, because then immediately you just write the things without really stopping and saying, this is that, immediately. It's a constant volume, there's no change in volume, there's no work. Part B, but what happens with energy? Well, in energy you have work plus heat. Now there's no work, so it's going to be zero, but there's heat, which is that. Now is heat done? Is heat transferred to the system or heat transfer from the system? Well, this goes from the system to the outside. So that heat needs to be negative, right? It's smaller than 0. So we have to say that the change in energy is going to be 465 10 to the 3, which is kilojoules, okay? and that's the change in energy. That's very simple. It's trivial. So where is that energy going if you wish? Again, we could see the same thing. Well, now energy we said is kinetic energy plus average kinetic energy plus the potential chemistry to say of binding energy, right? And so this is a gas, so we can let's say that we take this to be 0 because it's an ideal gas. For an ideal gas, there's no binding. It's one of the assumptions of the kinetic theory of gases. So everything is going to be going to kinetic energy. So what's happening here then? That the delta U, the change in internal energy, is smaller than 0, which means that the change in kinetic energy is negative, which means the temperature is decreasing, because we can just go step by step, but the change in kinetic energy is the final kinetic energy minus the initial kinetic energy, and if this is smaller than 0, means that the final kinetic energy is smaller than the initial kinetic energy, right? Which means that the kinetic energy is decreasing, and because kinetic energy is temperature, temperature is decreasing. So what happens when I lose heat? Well, when I'm losing heat, the temperature drops. That's it. Of course, I'm transferring heat out, right? Transferring heat out, so the internal energy drops, and so the temperature also drops, which is what we expect, of course. If I have some amount of heat here and we transfer it, if this was a bath of water at 50 Celsius and I drop a block of ice or a block of aluminum at 20, I expect the block of aluminum to extract heat from that water. Well, this is what we're discussing that. So what happens to the water as it transfers that heat? The temperature drops, right? So this is isochoric. It's just an example. There's isochoric. There's also isothermal. Isothermal means at the same temperature. You're going to have adiabatic, which are problems where there's no exchange of heat. There are different labels in here. Again, we're not interested in this introduction to physics, which is physics 2053. But it's worth maybe having an idea of some of those, particularly if you use them in thermodynamics. In chemistry. Obviously, in thermodynamics, you will have to study them. So this is basically the idea. But we see how everything gets connected. And thanks precisely to this understanding of microscopy, we start to make sense of the things that happen macroscopically. Now we understand what, of course, the temperature drops. Why? Because temperature is measurement of particles. If you make all this connection, many things are going to become very easy to understand very quickly, right? Anyway, let's see more problems. Problem number 3 is trivial. It says a heat engine does 9,200 joules of work per cycle while absorbing 25 kilocalories. And they're just do this to make it nice for us. So that's going to be in joules. So that's going to be 100 by the force. That's going to be something like that, maybe. Okay, we'll check it out. But anyway, basically this is the amount of joules that the system is put in. Let's make sure. So now the question is the efficiency. So let's go and let's make our diagram to understand exactly what's going on in here. We know we're extracting 9,200 joules of work per cycle, and we know as well that we are what's the word in say? Oh, this is very interesting. It says that absorbing 25 kilocalories of heat from a high temperature reservoir. So we are absorbing heat from the hot side. What is the efficiency of this engine? So potentially, of course, because we are educated on second law of thermodynamics, we know there needs to be some QC there. So what's the idea in here? We absorb this to produce that. What is the efficiency? So as we said, what I want, what I pay. What I want is work. What I pay is QH, right? Because if you go quickly to the formula and say, oh, the formula says that this is 1 minus QC over QH, now you have to figure out how much is QC, which you can and we will do in a second, just for the sake of completeness. But if you just use this equation, then efficiency becomes trivially what I extract is 9,000 divided by 200, and what I have to pay is 104,500. And so if you divide this by that, apparently you get 0.088, let's say, which is of course approximately 8.8%. So what is the efficiency of this system? 8%. Because we don't know the temperature differences, we cannot calculate Carnot ideal efficiency. This is the real efficiency. Carnot is going to be larger potentially, but this will never be smaller than, let's say, Carnot. excuse me, this will never be larger than Carnot, right? Because Carnot is the maximum, the best case scenario. Now, of course, because work, so we can make conservation of energy. So heat comes in, right? There is no change in energy, so which means that heat that comes in is QH, work goes out, and QC goes out. So QC is, of course, QH minus work. So if we had, and to rewrite that, we would have that this is 1 minus QH minus work divided by QH, which is, of course, 1 minus QH. This is 1 minus WQH. But what is that? That's 1 minus 1 plus, excuse me, this is plus, minus minus, plus work divided by QH, which is work divided by QH, which is exactly what we know if we just apply the definition of efficiency. So anyways, that's what we want, what we pay. Idea of efficiency, always, okay? How efficiently am I using the heat that I'm absorbing? Well, I'm using it with an 8.8% efficiency. One more problem. Problem number 5. It says the nuclear power plant operates at 65% of its maximum theoretical Carnot efficiency, right? So it's operating, let's write sub OP for operating, at 65%, which is 0.65, right? Because 65% is 65 divided by 100, 0.65. Of its maximum, by the way, 65 of the maximum, so it's actually, it's operating at 65%. Let's write it step by step. 65% of the ideal, which means it's the same as 0.65 of E sub ideal, right? Of efficiency between, okay. And this happens when it goes at hot temperature of 660 Celsius and cold temperature of 330 Celsius. And very important, as soon as you see Celsius, you start to not panic. There's no need to panic, but let's start to be careful because we need to convert this into Kelvin if we're going to be able to. So this is going to be plus 273, which is going to be 833 Kelvin, and this is going to be 603 Kelvin. Okay, very good. When this is operating at this range of temperatures, this is the efficiency. And since the plant produces electric energy at the rate of 1 gigawatt, and by the way, gigawatt of course is power, right? Remember that power, we just describe as P, is energy over time, right? And the units of this is watt. Why watt? In honor of James Watt, right? Okay, we just discussed in the introduction. Very good. So, how much exhaust heat is discharged per hour? So this is joules per second, right? This is 1.4 giga, 10 to the 9, joules per second. And so, because we want to do it, let's keep it as it is right now. Okay, so a nuclear plant operates at 65% of efficiency, of the maximum theoretical efficiency. So the first question is, how much is the actual operating efficiency? So let's find the maximum operating efficiency. I don't know what I did there, that's just the real, let's say. The operational efficiency is going to be 0.65 ideal. How much is the ideal? Well, it's given by Carnot, cold divided by hot, which is going to be 1 minus 603 divided by 933. And if we make these numbers, it's about 1/3. So it's going to be about 0.67, something like that. So it's 0.33. Okay, so the ideal is 0.33 and we're operating at 65. So the operating efficiency is going to 1/3, let's say. Okay, because this is 2/3 minus 1 minus 2/3, 1/3. So that's going to be 0.65 times 1/3, which is going to be no, that's going to be 0.2, we're generous, let's say 0.22, okay? So it's about 22% efficiency. Okay, that's the operating efficiency. Now the question is, this is the operating efficiency, we got operating efficiency, and we say how much energy, how much heat is discharged per hour. So let's see. Oh, it's discharged, so it's actually much more interesting. Okay, so then let's see the total power. So let's write down here a diagram. We are interested in how much is this heat, and we know this. And so of course we know the QH, which is the in, needs to be equal to power, or let's say of work, right, going out, plus this, which is discharged. So we can calculate this. Well, this is given. This is that one. Work is this times time. We can divide everything by time. And this heat is what we need to calculate now, right? So how do we calculate that anyways? And this. So we have the total. Yeah. So let's think from the perspective of conservation of energy. This is the energy that we put in. This is the energy that we extract, which is the power. And this is the energy that we discharge, which is the waste. Because the system is operating at 22%, we can figure out how much comes in based on the fact that the efficiency for a real engine is what I obtain or what I want, which in this case is work, divided by what I pay, which is QH. And this is 0.22, which means the QH is work divided by 0.22. Work is this amount of power. It's going to be power, not work, but basically it's going to be 1.4 10 to the 9 joules per second divided by 0.22. If we make that number, we can find the solution somewhere. That's going to be the QH. We can find QH to be 6.1 10 to the 9 joules per second. Okay, that's the heat that we need to put in. That makes sense. Okay, so we put 6.1 gigajoules per second, or gigawatts, to produce 1.4 gigawatt. What's going on everything else? Well, everything else is being wasted. So we have it over here. So we can just solve and say the QC, it's equal to QH, which is the total absorption of heat, which is going to be produced by the nuclear reaction, of course, minus the work produced by the steam on the turbine, blah, blah, blah. Okay? And so we make those numbers. It's going to be 6.1 gigawatts minus the work, which is 1.4 gigawatt, and that's going to be 4.7 gigawatt. So how much heat is discharged? 4.7 giga. This is not a 6, this is a G. So it's gigawatt, okay? And so it's 4.7 gigawatt. Here's the thing, the question is about in hours, I think. So how much exhaust heat is discharged per hour? Let's maybe make it here in this room, over here in this portion. The power of heat, so one of the things we didn't do, but work is, instead of doing this, we could have instead of heat, we could have drawn power heat, power work, and heat and power cold, right? Power hot, power cold, power, and what we have obtained is not QC, it's not QH, it will be PC, right? And sorry, this is PC, QC, right? So now if I want to know the power in how much is exhausted per hour, this is per second. So the QC, let's say, is gonna be 4.7 10 to the 9 joules per second, but now I want per hour, and I know there is 360 seconds per hour, and so then I can just make that correct, and so we have to multiply that, which is about 1.7 10 to the 13 joules per hour. So if we were to calculate 1 hour, then you would be producing 1.7 10 to the 13 joules. Now, a good question is how much energy is that? So something we could ask ourselves is, out of curiosity, of course, because we want to go beyond what we've been demanded. We just want to anchor things and link stuff. So again, it's a different scenario, okay? So this is just in terms of power, because remember, the power is just energy over time. So we can also define the equivalent of power for heat over time, okay? And the same thing, power, we can say is work over time. Right, we can do that. So that's what we're saying over here. I'm calling everything Q and P which is technically not correct. I'm being very lax here with the notation. I shouldn't have, but anyways, the idea is understood. This is power in reality, it's not heat, it's power. So we can find power cold, power hot, and so we find that's the match. So we could ask ourselves, how much water could we boil with that, for instance, or how much water could we boil, or how much ice could we melt, or something like that, or how many kilometers, how many, something like that, kilometers a car can perform. And because now we have an energy per hour, it means that every hour it will be giving 1.7 10 to the 13, and that's actually terajoules. So 17 terajoules per hour does that factory do. So that means that if you count for all the processes in the neighborhood of that plant and assume there is perfect ideal transmission of that power, you can feed out, everyone around the plant can consume up to 17 terajoules every hour, right? It's amazing, basically. So that's why we use power plants, because they don't just feed one person, feeds a lot. So you could calculate how much water, how many meter cubes of water could you boil with this, right? If the water was at 100 degrees, it would be just simply m divided by L, okay? Or say how many liters you can make it go from room temperature to boiling water, right? Not boiling it completely, but just like raise the temperature. So things like that, because now you have actually a way of calculating heat, and see, basically, see how much power is that, maybe compare it to how much power your car requires per hour, and see how many cars can be fed by these, stuff like that. When you study in physics 2 electricity electronics, you're going to see also the idea of batteries probably. And so you could see some of this power maybe we can use to charge batteries, which generates potential energy, electric potential energy that will be later on be used by a battery in a car. And so you could see how many kilometers with how many cars can this provide for, right? But these are just idea. Standard plants, any plant doesn't work at the ideal level. It always operates at a lower level. The closer, the better, right? 65 might not be that bad. But look at the end of the day, that means it's just 22% of efficiency, which is almost per every joule that you generate, you're losing 4, right? Well, actually 6 in this case, 5, no? 2 to 10, right? So it's because 22%, 1 to 5. So that's that one of work per 5 of discharge, which is basically what we've obtained here, right? This is 4.7, which is about 5, and the work that we are putting is 1.4, about. Okay, so as this is the idea in here, we have to pay a price to produce energy. Towards the end, when we see a little bit more detail of entropy in the particular example, we're going to see trying to make a final comment on how entropy is related to available energy. The problem is not energy. There's no violation of energy in here. We had this much energy. In fact, we forced conservation of energy, and we have extracted something. Whatever is not extracted needs to keep going. The problem here is once you are wasting all this energy, that energy goes into a different system. And so we're just losing, let's say, available energy to actually perform work. And that's the problem of wasting energy, so to speak, is once the water is in the dam, is full, we'll say this again anyway, you open the dam and then moves the turbine, but as soon as it goes to the ground, that has lost the energy cannot be recovered, right? You would have to do work to put it up again, but it's lost. So in a sense, you're losing available energy that is available to use work, and this idea again is captured through this microscopic understanding with the statistical understanding of entropy from Boltzmann equation. We'll see that towards the end. Let's see more examples. So let's see problem number 6 in discussion. It says there is a 4-cylinder gasoline engine with an efficiency of 0.22 that delivers 180 joules of work per cycle per cylinder. So we have work is 180 joules per cycle per cylinder, right? Correct. If the engine runs at 25 cycles per second, which is the same as 1500 revolutions per minute, determine the work done per second. So the first thing we're going to have to find is what is the work done per second. Work per second. Okay? So to answer the works per second, we have to figure out that we have a 4-cylinder,
engine, right, which is one, well, it depends on the thing, but basically they're going to be just oscillating, going up and down with explosions. So we're going to see, okay, how much work per second is produced. Well, we have H1 is going to 25 cycles per second, and H1 is 100 joules. So we can say work per second, right, is going to be in 1 second, is going to be what? The work, which is joules cycle cylinder. Now we're going to get rid of the cylinder, so we have to multiply times 4 cylinder. So cylinder and cylinder will cancel. And each one of the cylinders is going at 25 cycles per second. And so cycles and cycles cancel. So you see we end up having joules per second. So basically this is the same as 180 times 4 times 25 joules per second. This is 100, so this is 1800 joules per second. So this is the first solution, or 18 kilojoules per second. Okay, the second question is going to be the total heat input per second from the gasoline. The total heat input from the gasoline. So if we make the engine a box, we're going to say that there's heat coming in and work going out, and there's going to be some of the heat going out, which is going to go to the exhaust of your car, right? That's the idea. By the way, if the environment was at the same temperature, of course we would be all dead. But if the environment was at the same temperature as the engine, then we wouldn't be able to produce any work whatsoever, because the only time there is flow of energy is when both of those are at different temperatures. Naturally, although we would have to have work to make the flow, but the entire purpose of an engine is to extract work. So if you have to put work, what are we talking about, right? It's not a heat engine anymore. Okay, so that's just an idea here. So the idea here is now the total heat input per second from the gasoline. How do we figure out that thing? Well, we have the efficiency. What is the efficiency of a heat engine? Is what I want, which is work, divided by what I have to pay, which is the heat. Whenever you write in efficiencies, by the way, don't put the signs in the heat, because they are already integrated in the formula, right? That's to say, heat is always going to be positive, and cold is going to be always taken as positive, whatever it is, because we already wrote these formulas based on the fact that this is going out and this is going in, okay? But anyway, the efficiency, this is 0.22, which means we know that, and we want to know how much is QH. So what we can do is just take QH and say the QH is work divided by efficiency, which is 18 divided by 0.22. Right, which is going to be, it's about 8.1 10 to the 4, okay? 10 joules per second. Okay, so how much heat do we take is 8.1 10 to the 4 joules per second. And finally, since if the energy content of gasoline is 130 megajoules per gallon, so 1 gallon of gasoline is 130 10 to the 6 joules, how long does 1 gallon last? So basically, this is 1 gallon, and this is the heat that we need. So we need to burn enough gasoline to input this heat to extract this work. This is the idea. We burn the gasoline to put the heat to extract the work and exhaust the discharge. So then, that means that we can divide the 1 gallon, by the amount of heat we need to get that, which is 130 10 to the 6 divided by 8.1 10 to the 4, and that's going to give us 1,600 seconds, which if we divide by 60 and then by 60 again, so by 360 basically, it's about half an hour, right? Because 1800 is half an hour, so it's about 0.45 hours. So how long would you be able to run the car? Your 4-engine car is for for about half an hour for 1 gallon. So 1 gallon would take you at this rate, of course. And there's the thing, everything, it comes with 1500 revolutions per minute. What happens if you want to go faster? Well, engines have, it's engineering, but engines has usually like a range of revolutions per minute where they're efficient, or they're more efficient, let's say. Engines at low revolutions or at very high revolutions, they're not very efficient. So although you can go at higher revolutions, the amount of work is going to be much lower. And so when you go very fast and you rev your engine, you go 3,000 or 4,000 revolutions per minute. It depends on the model anyways. But compact cars, particularly high revolutions per minute, is going to mean that the efficiency is going to drop, so it wouldn't last half an hour, maybe it lasts 15 minutes, right? So that's the idea of efficiency also related to this. This is kind of the ideal scenario. And if you are running, excuse me, a manual car, that's why you change the gears whenever you're the revolutions are going to tell you when you have to change the gears to extract proper amount of work without loss of efficiency, right? But that's the idea of gears. We of course we don't discuss in this course. But basically, this is the idea. We want to get work out. How do we get work out in a combustion engine? By burning gasoline that releases the internal energy of the gasoline is released in the form of heat that uses the engine to output work and then throw coal. Look at this, by the way. We need to take 81,000 joules to produce 180 joules. This is something, right? So this is the efficiency that we have in these systems, okay? Which, by the way, I made a mistake. This should be then 10 to the 3, no? Oh, because this is the work for yeah. Here this is per cylinder per cycle. Okay. So very good. Anyways, to produce 18 kilojoules, we're burning 81 kilojoules. So to produce 18,000 kilojoules or 18,000 joules of work, we need to provide 81,000 because the efficiency is 22%, right? If you multiply times 100, that's going to give you then 22%. So this is the idea for percentage in efficiency. Anyway, this is for engines. Let's see more examples. Problem number 8 in discussions is a heat pump problem. So it says a heat pump is used to keep the house warm at 22 degrees. Of course, any house is not properly isolated, so there's always going to be losses to the environment. And so that's the one that your heat pump is trying typically to control. So it's going to be cold outside and it's going to be warm out inside, and you're going to have a heat pump, HP heat pump, to control that. And since a heat pump is used to keep the house warm at 22 Celsius. How much work is required of the pump to deliver 3,800 joules of heat to the house if the outdoor temperature is 0 or minus 15? Okay, let's start with the first one. So how much work do we need if temperature outside is 0 Celsius? Okay, let's figure that one out. So let's do it in here. What we're trying to do in our house, we're inside, we're trying to get heat from the outside and bring it inside. We're not producing heat in a heat pump, we're just taking heat that already exists and put it in there. We just said that as the difference between a resistive heater or a stove or something like that, where you're actually creating that heat. In this case, we're just taking that heat from the outside and putting it inside, okay? And so the thing that we're trying to do is take heat from the cold side and through the heat pump that produces work, deliver it into the hot side, which is where we are, okay? So what is going to be the efficiency? Well, the efficiency is the coefficient of performance, which is another way of saying what I want is QH, because I want to warm my house. What I have to pay is work, right? Okay, there is an addition that says assume, I forgot that part, that the coefficient of performance is 3, okay? That was the critical part. Therefore, work is going to be heat divided by the coefficient of performance, which is going to be how much heat we're putting is 3,100 divided by 3, and that's going to be 1,030, let's say, joules. So how much work do I need to put? 1,000, correct, 1,003 joules. So this is why it's much more efficient, typically, depends again on the scenario, we're going to see that. It's much more efficient typically to bring the heat from the outside and actually produce it. Because to produce this amount of heat, we would have to have 3,100, but now we're not producing it, we're just transferring it, okay? Okay, says how much work is required to deliver into the house. Okay, very good. Now, The calculation, this is going to happen a lot. Well, this has happened by this time, you know it already. This happens a lot in problems, and if you have a standardized test, you're going to experience it a lot. Now, the next question is going to be saying, okay, what is the work at minus 15 Celsius, okay? If the outside is at minus 15 Celsius. And here's the thing. Is the coefficient of performance different? No. Is the amount of heat that we want different? No, because we are trying to warm up ourselves, and that doesn't depend on the outside, it just depends on my internal system. So the amount of heat is the same. Heat capacity and mass has not changed. Therefore, I require the same amount of heat to actually have certain temperature. And therefore, does then work change? No, it doesn't. So work is, of course, the same. Work is going to be as the ratio of heat required by the coefficient of performance, which is 3000 divided by 3, which is 1030 joules. So it does not depend on temperature. The amount of work I need does not depend on temperature. Why is it very important? We're going to have to take heat from the outside and put it into the inside. Here is the next question, which is important. Redo for both temperatures, assuming an ideal coefficient of performance. The ideal coefficient of performance for a heat pump is the equivalent of a Carnot, but now for the reverse cycle, right? Is given by the ratio of the hot side divided by the difference hot and cold. And now it's very important to remember that this needs to be in Kelvin. So we're going to have two scenarios. Let's say the first one on A is when we have 22 degrees is going to become 295 Kelvin. 0 degrees is going to become 273 Kelvin. And minus 15 degrees is going to be 258 Kelvin. So we can write for the case A, we're going to have the hot side is at 295, the hot side 295, cold side 273. So this is the same as 295 divided by 22, which is going to be 13, let's say. If we're trying to do the coefficient for the case of B, which was minus 15, the hot side is still 295, the cold side now is 258. So if you make this, you're going to find something about 8. So then we see the difference in coefficient of performance for the ideal and the Carnot ideal for the coefficient of performance for ideal case for 0 outside and also minus 15 outside. Now what has changed, what is changing now? What's changing is the ideal gives us the best performance that we can have. When it's 0 outside, the best is 13. We're only at 3. When it's minus 15, the performance drops. We expected that because there's less heat outside when you're at minus 15 Celsius, and therefore it's much more difficult, let's say, to take work, right? And then the coefficient is 3, so still we're actually having a heat pump that's far from being ideal. But the question here is to say how much work then we would be actually, how much work would we require in those scenarios. So if we had the case of coefficient of 13, we could just see, let's do it here. It's going to be QH divided by and that's going to be 3,100 divided by the coefficient of performance, which is 13. And so that's going to be, let's say, 230. And in the case of joules, and in the case of minus 15 outside, the coefficient of performance is now 8. So it's going to be 38, which is going to be joules. So something like that. Okay, approx, it doesn't matter. What's important in here? See, as we drop the coefficient of performance, this is, let's say, 0, and this is minus 15. Coefficient of performance. As we drop the coefficient of performance, the amount of work that we need to put to extract that heat increases. For a coefficient of 3, we need 1000 joules. For a coefficient of 13, we need 230. For a coefficient of 8, we need 400 joules. Why is that? Why is the coefficient of performance decreasing? Well, from ideal, we can actually get a better idea. Because the colder it's outside, this number is going to become larger, the denominator. And so the coefficient of performance is going to drop. Well, we can understand microscopically also, or from a point of view of conservation, why it's different. Heat pump is just pumping heat, literally. That's why it's called heat pump, right? So it's taking heat from somewhere that exists and bring it somewhere that already exists. But you have to find it outside, and outside is colder. So, because regardless whether it's outside or not, you're taking it from the outside. And outside, the colder it is, the less heat it has available. Because if I have something at 0 degrees and I want to put it at minus 15, I need to take heat. So something at minus 15 has an environment at minus 15 with the same amount of matter, blah, 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 blah. But it have less energy available than at 0. So obviously, it's much more difficult to find. It's like, oh, where's the heat here, right? I'm trying to find it. So the colder it is, the less energy there's available, so the more difficult it's going to be, so the worse the performance is going to be, right? To the point at some point where you're going to have a coefficient of performance 1, and what would that mean? That the entire heat that you're bringing is heat that you put in work. But at that point, obviously, right, if the entire heat that you're bringing in is the same as work, that's exactly the same as taking an electrical stove or something, because the work to produce that heat is the work itself. So at that point, the coefficient of at that point it would make sense to have a heat pump. But a heat pump, again, that's the analogy we were trying to make before. It is comparing building a car from actually moving a car from somewhere that exists where somewhere you need, right? So if I need to move now and I need a car, I can build my own car, which would be just saying I burn the gasoline to generate the heat, or I turn on my electric heater, right? That's building the car. The electric heater builds or creates that heat, creates, quote unquote, of course, creates that heat. In the case of a heat pump, I'm not creating the heat. I'm just going somewhere to parking lot and bringing the car. So that's the work I'm doing. I'm taking something that already exists, so to speak, right? That's the idea of a heat pump. And the same thing is going to happen somehow with the refrigeration, just that we're not observing from the point of view of we're interested in transferring to the hot, we're interested in transferring from the cold. That's the idea, or that's the difference between the refrigeration and heat pump. But this is basically the idea. It's actually very interesting because we understand then some things that might be a little bit weird, but we'll see them. Of course, in a heat pump, you're taking the heat from the outside. The colder it's outside means the less heat, means more difficult it's going to be to take the heat, means more work I'm going to need. Let's see problem number 13 on calculating entropies in a system. It says that we have 1 kilogram of water. Let's say there's 1 kilogram of water at 35 Celsius. And then we have another, which is 1 kilogram of water at 45 Celsius. And then we say we put them inside a well-insulated container. So basically we are assuming that it's isolated. And we want to see what's the change in entropy of the system. So we're going to put these both inside here. Now, of course, the first thing that we need to say is that we know that the change in temperature, the change in entropy is going to be the heat divided by temperature. But the change of what? We have to consider system 1. This is the system is composed now of water 1 plus water 2. And so what we can actually see is that the change in entropy is going to be the total change in entropy is going to be the change in entropy in 1 plus the change in entropy in 2. Okay, so the first thing that we need to figure out, however, is what's going to be the thermal equilibrium of these things. So we need to see what happens when I put these two things together. And of course, the heat that one gives needs to be received by the other. In other words, that because there's no change in energy, the change in heat plus the change in work, but there's no work, of course, right? That's going to be the change in energy, which is heat plus work, needs to be 0. Now, who's putting nothing is putting work in here, so we just have heat of 1, maybe heat from 1 plus heat of 2 needs to be equal to 0. Now, how much is heat of 1? Well, heat of 1 is going to be mass 1 of water, specific heat of water, and the change in temperature, and Q2 is going to be the mass of 2, C of water, specific heat of water, and the change in temperature. The specific heat of water, the specific heat of water, as we know, is 1 calorie which is the same to say 4,180 joules per kilogram per Kelvin. Okay. Okay. In Kelvin, plus 273, so that's going to be correct 308, and this is going to be 318 because it's 10 degrees more, correct? Without this, this is just in Kelvin. So what's going to happen is that the temperature is going to be putting both together. What we know is that the hot is going to give to the cold, basically, but let's pretend even that we don't know that. But that's going to be that 0, it's equal to mass, which is 1 kilogram, mass 1, C of water, delta T, for 1, plus mass 2, C of water, delta T of 2. Now C of water is going to cancel anyways, and the masses are the same, so they're actually 1 kilogram, right? Because mass 1 is the same as mass 2, which is just the mass, which is 1 kilogram. So actually we can just simply write that 0 is equal to the change of temperature in 1 plus the change in temperature in 2. And we can write this as final equilibrium temperature minus T1 plus final temperature in equilibrium minus T2, which is the same to say that we can put T1 and T2 there, so twice the temperature in equilibrium, twice the temperature in equilibrium is going to be equal to T1 plus T2. And how much is that? That's 626 Kelvin. What that means is that the temperature of equilibrium is half of that, which is 318 Kelvin. So the equilibrium temperature is 318 Kelvin. That was the first step. We figured out that the thermal equilibrium is reached at 300 okay, there's an error somewhere here. (313) 313 Kelvin. 313 Kelvin, which is 5 way between, because they're 10 degrees. We could have expected they're going to meet at the halfway point because there's the same liquid, the same mass, so it's going to be halfway point, which is 313 Kelvin. Okay, now we can calculate the change in temperature in each of these cases, right? Change in temperature in 1 is going to be 330 minus 38, which is 5 Kelvin. Change in temperature 2 is going to be 313 minus 318, which is minus 5 Kelvin. And we start to see something interesting in here, right? So now we're going to see what is the change in energy. So we can find how much is change in energy. So for Q1, change in energy is going to be mass water delta T1, which is going to be 1 times 4,180 times the change in temperature, which is 5. And for the other one, for Q2, is going to be mass CW delta T2, and that's going to be 1 times 4,180, and now minus 5. So how much is this? That's going to be 4,000 times 5, which is 20.9 10 to the 3 joules, and this is going to be minus 20.9 10 to the 3 joules. Good sanity check that the heat that one gets it from the other one. Obviously, otherwise there will be no balance of energy. Now we have this heat. Let's erase this and rewrite now for entropies. So the change in entropy is going to be the change in entropy of the total change in entropy is going to be the change in entropy due to the first system plus the second one, or the first bucket with water with the second one. The first one is going to be the change of heat, the heat 1 and temperature 1. Now, what is heat 1? So here. So it's going to be 20.9 10 to the 3, and then divided by the temperature in 1. Now, the temperature 1 is not, we could take as an approximation to 1, but in reality what we have to take is the average of the equilibrium temperature. So we should write something like that. It's because it's a characteristic temperature, not actually the temperature, right? So we should say here like, yeah, the temperature. So let's say it's going to be 3, it's going to be basically this. Let's write it first explicitly. Let's write it here. First, the temperature we're going to plug is the equilibrium temperature plus the initial temperature divided by 2. And then we can call this like the average temperature if you wish, okay? So then when we calculate the change in entropy of 1, it's going to be the heating 1, and then the average temperature in 1. So what's going to be the heating 1? 20.9 10 to the 3. And what's the average temperature? Is going to be the initial temperature, which was 308, plus the final temperature, which is 313, divided by 2. That's going to be 41.8 10 to the 3 divided by 624. Excuse me, 621. What about delta S2? It's going to be heat 2 and the average, let's say, temperature 2, which is going to be minus 20.9 10 to the 3. And now it's going to be 318 plus 313. And so this is going to be divided by 2. And this is going to be minus 41.8, excuse me, 10 to the 3 divided by 631. So from here we're already seeing that denominators are the same, denominators are different. This is larger than this one, so this is going to have a smaller negative number than this one, right? And so now we can just finally write the total entropy as the sum of both is going to be, we can write it 41.8 10 to the 3 divided by 621 plus or minus delta S2, let's write directly minus 41.8 10 to the 3 631. And if we make this operation, we're going to find 1.06 joules per Kelvin. So what is the change in entropy? The change in entropy is larger than 0. Of course, that's what we expect from the second law of thermodynamics. And this expresses why the heat is flowing from one to the other. Let's quickly show what would happen and why we don't expect, for instance, that heats reach another one. So here's the thing. We can say just conceptually, but you can actually numerically make the numbers. Let's say you were mixing 35 with 45 degrees. We can calculate what would be the case. Well, this is the end of the problem, right? We could calculate what is the case when 45, instead of going to the equilibrium temperature, which is halfway through, let's say this reaches 50. And once we fix that, through conservation of energy, we could say, hey, how cold will this be? And this is going to have to be colder than 35 to conserve energy. But if we make that, that would mean that the heat is going from hot to cold. And we will see that the total entropy is going to be negative. Let's do it just for the sake of the experiment. If you don't want to see, you can skip it basically. This is the answer for this problem. What is the total energy of the system? It's increasing. The entropy of the system is increasing. The entropy of the system is decreasing. Can the entropy of a system decrease? Yes. But the total entropy of the system plus the surroundings, or the universe, the entire universe, which is the total entropy, always must be larger or equal to 0. Equal to 0 is only going to be when it's reversible, right? And this is a natural process. There's not, in here, heat is going to flow from here to here, right? Because this is hot and this is cold. Heat is going to flow from here. By flowing heat, temperature drops, temperature raises, equilibrium temperature. Let's see why couldn't we have the case where energy flows in a different direction. Let's quickly erase here. So let's say now that the equilibrium temperature we choose is to be, well, no equilibrium temperature actually. Let's imagine there was a scenario from the point of view of this one, where this, instead of going to 3013, which we said was the equilibrium temperature, let's say that what happens is that I put them together and now there's a mass of water instead of at 40 degrees Celsius for both, which is this one, 30, this is 14 Celsius. Instead of that, I'm going to say that this warms up because it takes heat from here. Because that's the way that heat pump works. And I say, why do I need to put work? I know heat pump, I put work. Why? Well, of course, the answer is the second law of thermodynamics. But I say, why? Okay, let's pretend that the equilibrium temperature now for this second system, this system is going to go from 45 to a final temperature of 50 Celsius, which is to say that the second temperature final in Kelvin is going to be 323 Kelvin. And then based on conservation of energy, because I want to have the energy equal to 0, that means that Q1 plus Q2 needs to be 0. Now, how much is Q2 now? Is the change in temperature there. So it's going to be mass, CW, and now delta T. Delta T now is 5 Kelvin, positive 5 Kelvin. Okay, that's delta T. Delta T. So I can put the numbers. I'm not going to write the mass or CW because they're the same, but now I have a positive 5 Kelvin. And I'm asking how much should be the final temperature in T1. Okay, So then I can say that Q1 needs to be equal to Q2. So Q1 needs to be minus Q2, which is the same as saying the same mass CW, but now minus 5 Kelvin. Which means that this one reduces to minus 5 Kelvin, which means this one ends up being in temperature 1 final, let's say, right? That means that delta T for 1 needs to be minus 5 Kelvin, which means that the temperature 1 needs to be temperature 1 plus 5 Kelvin, minus 5 Kelvin. And that simply represents 308 minus 5, which is 303, which is exactly the same as 30 Celsius. And now I'm asking myself, okay, according to conservation of energy, this can reduce 5 degrees if this increases 5 degrees. And I have the same energy because the energy that this guy has lost has been earned or absorbed by the hot side. And according to the first law of thermodynamics, there's no reason why this shouldn't happen, or this couldn't happen, because it is conserving energy. We forced it ourselves, actually. So it is conserving energy. The energy lost in here has been absorbed in there. But why don't we observe that? Second law of thermodynamics is telling you, according to Clausius, that needs to be equal or larger than 0. Let's calculate what will be the change in entropy in here. Now, we're going to have an average temperature for 1, which is going to be 308 plus 303 divided by 2, which is going to be 305.5. And then we're going to have a temperature 2, which is going to be 318 plus 323, 3 divided by 2, which is going to be 320.5 Kelvin, right? Because they're 5 apart, so it's just simply 2.5 extra. Okay, so we have those average temperatures. Let's calculate what is the change in entropy. In 1. In system 1, the change in entropy is going to be Q divided by T1. Let's calculate heat, we didn't do, right? But heat is going to be mass CW times that. So it's going to be mass CW and then minus 5 Kelvin. Excuse me. Q2 is going to be 5 Kelvin, positive 5 Kelvin, because it's a positive change in, it's a change in temperature. And oh no, this is system 1, sorry, this is system 1. This is 1 and this is 2, right? So system 1 is going to be the change in temperature in 1. And the change in temperature in 1, we didn't write it, but the change in temperature in 1, of course, is minus 5 Kelvin. The change in temperature in 2 is positive 5 Kelvin. And this is going to be divided by T1, which is the average. And that's how much? That's going to be 1 kilogram for 180 times minus 5 divided by 305.5 Kelvin. What about the change in 2? QT2, the heat is going to be mCW delta T, 2, which is divided by the average 2, which is the same as 1 for 180 positive 5 Kelvin divided by 320.5. And now I can put the numbers together. How much is delta S1? How much would be delta S1? So this over here, if you make the number, is minus 68.4. And how much is delta S2, which is coming from here? That's going to be 65.2. How much is this? Negative 65, that's going to be negative 3.2 joules per Kelvin. The change in total entropy is smaller than 0. That is forbidden by the the second law of thermodynamics. Why do things do not become hotter and cold things colder when they're in contact? Why heat flows from the hot to the cold side? Because the change in entropy then will be negative. And then we have made this system says entropy, this law, which is all systems naturally go to larger entropy. If you actually want to violate, so to speak, this, it's just because in your system is not isolated. Something from the outside in the form of work, it's coming in. That's refrigeration, that's a heat pump. Otherwise, impossible. And now we're going to see the statistical reason why. We could have done this more simply, which is realizing anyways that this is inverse with the temperature and the heat is the same. So what matters is going to be this temperature over here, but I would have been too symbolic. It's interesting to see a particular case. But why this is always happening, we have it from the statistical interpretation. Let's do the last example of this chapter, and let's do also see last comments on entropy. Last problem in this chapter, problem number 14. It says there is a system containing of 3 coins that can come up either as heads or tails, right? These are 2 options. They can go as heads or they can go as tail, each one of those. In how many different ways can the system have all heads up or tails up, 1 tail and 2 heads up, 2 tails and 1 head up? The best way to see this is just to make a table. So let's make a table of this. The table is going to be organized with the possible results. And it's a very important thing here is that every coin is indistinguishable. Which means that we cannot distinguish them. So what that means is that if I have this coin 1, 2, 3, it will be the same as having 2, 1, 3 or 3 to 1 or any other thing. We're not concerned about the order. We're only concerned about the state of that coin. And what we're saying is what can we discuss? What we can discuss is there's 3 options. Each one of those can be head or tails, can be head or tails. So all the combinations that exist in here, you can write them yourself, but those are heads, 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 tails, heads, head, tails, 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 heads, heads, tails, and so forth. So actually you can find all the combinations possible, right? But you can, let's actually do them. Specifically, we're going to do for this example. Next time you would not be expected to do this. Even if you know, of course, statistics and combinatorics, then this is much more trivial. But let's pretend that that's something we don't know. Okay, let's do it from the ground up. So we just see. How many combinations we have? Well, we're going to have first, we can make a decision tree, so to speak. Okay, so the first coin, let's say. First coin can be heads or can be tails. Now the second coin can be heads or can be tails. And the third coin then, with the second coin being that or that, and then with the third coin being heads or being tails, right? So this is going to be the step where we put the 3. So that's too high. Let's bring it down. Let's make the decision tree over here. First coin can be, first coin, let's say this, here we decided coin number 1 can be heads or can be tails. So the second coin can be heads or tails, can be heads or tails. This is for the second. And the third one can be heads or tails, heads, tails, heads, tails, heads, tails. So let's count how many options do we have. 1, 2, 3, 4, 5, 6, 7, 8. As expected, 2 to the power of 3. 2 possibilities 3 times. 2 times 2 times 2, 8, right? But anyway, let's pretend that we don't know anything. So let's write this result. This result actually corresponds to heads, heads, heads. This heads, heads, tail. This heads, tails, heads. Heads, tails, tails. And let's stop saying because it's lost the meaning. The heads there. Tails, tail, heads, tails, tails, heads. Okay, these are all the possibilities that are available in your system. What else can we do over here? Well, we can arrange them. Listen, we're going to put a table in here. Let's do it. Result, let's write. Let's make a table. Okay, result. 3 times heads. And look, I'm going to write 3 times heads instead of saying heads, 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 because some people are going to be confused and thinking that head, tails, heads is somehow different from tails, heads, heads. But it's not. This is much more easier to see if we write 2 heads, 1 tail. Then we realize that this is the same as 2 heads, 1 tail. So these are the same. If they're not in the same order, it doesn't matter. To avoid that, let's write it this way. So we have 3 times heads. And how many times do we observe it? How many times do we observe it? Well, 3 heads only happens here, not here, not here, not here, not here, blah, blah, blah. Okay? So that just happens once. What about 2 heads and 1 tail? Well, 2 heads and 1 tail happens here, 2 heads and 1 tail, 2 heads and 1 tail, that's it. So happens 1, 2, 3, 3 times. What about 1 head and 2 tails? So that happens here, happens here, and here. So we have 3. And what about 3 times tails? Well, that happens none of this, just here. So that's just 1. How many times do the results happen? 8. How many different options or combinations we have? 4. And here's the distinction we're making with Boltzmann law. To this, we call macro states. To this, we call the micro states. Because these are the different amount of configurations that produce exactly the same system. Why? Because 2 heads and 1 tail is the same. Whether I have heads, heads, tails, heads, tails, head, tails, heads, heads, all 3 represent the same macro system, which is 2 heads, 1 tail. All of these are microstates corresponding to the same macro state. This is macro, this is micro. This is our macrostates, these are microstates. What's Boltzmann telling you? Boltzmann is telling you that the absolute entropy of a system is given by the Boltzmann constant times the logarithm of natural logarithm of the number of microstates for a given macrostate, which means that I can calculate the entropy of these systems. The entropy for this macrostate is given by, for a macrostate, is given by the number of microstates. So that's going to be kb logarithm of number of microstates, number 1. Let's erase this, let's make it a little bit larger. This one, this macrostate, which is 2 heads, 1 tail, which is the same as 1 tail, 2 heads, which is the same. It's just I need to have 2 heads and 1 tail in any order. It doesn't matter the order. How this is going to be kb logarithm of number of microstates. How many microstates correspond to this macrostate? To this macrostates correspond 3 microstates. What about this one? Well, it's going to be, for these macrostates corresponds 3 microstates. What about this one? For this macrostate, there's only 1 microstate. We can make the numbers anyways, but we can see something over here. This is going to be 0, because logarithm of 0 is of 1 is 0. But before we do that, well, actually, let's do it. Let's erase this 1 second. Let's do this. Actually, sorry. Let's say this is equal to, this is equal to 0, this is equal to 0, this is equal to something else, which is going to be proportional to 1.02. So that's going to be 1.02 kb. I'm going to keep kb because we don't gain anything by writing this explicit resolution. Okay, we're going to add an extra column here. We're going to call it the probability of the macrostate. What is the probability of finding this macrostate? Is 1 out of the 8 microstates. What is the probability of finding a particular microstate? It's going to be equal to the sum of all the microstates corresponding to that macrostate divided by the total number of microstates. So what's the probability of finding this macrostate? Is the number of times that macrostate happens, which is just 1, divided by the total number of microstates, which is 8. The probability of finding this, then it's going to be 3, because 3 is the number of microstates corresponding to that macrostate divided by 8. 3 divided by 8, this is equal to 1 divided by 8. Of course, if you add all together, 4, 7, 8 out 8, that's equal to 1, okay? Don't need to add anything here. Okay, so what do we observe? There are states that have a higher probability of happening than others. What Boltzmann is telling you, that if you look at that, is that the entropy is proportional actually to that probability anyways. Mathematically it is anyways. It's proportional to the probability. Probabilities higher have higher entropy. So what do we understand when we're talking about entropy as disorder or order? Why would we say that things tend to disorder? These systems are more disordered than these systems. We consider everything heads up or everything tails more order or more disorder. How can we see that? Instead of taking 3 coins, take 100 of those coins, put them all the 100 coins all heads up, put them on a tray, shake the tray, and see how the coins fall. Do you really expect that all 100 are going to fall as heads or tails? No, you don't. You can actually calculate the probability. Is that non-zero probability? No, it's not. But the chances actually of finding that, the higher the number of particles, the higher number of macrostates, the higher the number of microstates. And so you're going to find that there is only one microstate that corresponds to this macrostate, and we have only different macrostates. But we had 100, or if, let's say, if we had, this is 1 over 2, excuse me, this is 4 different macrostates, because I don't want to use statistics number, but you can calculate this number and this number anyways. And you're going to see that this number increases, of course, with the number of particles that we're considering. In this case, the coins represent a particle. The number of particles I have, the higher the number of macrostates. But the number of microstates increases much faster than the number of macrostates. The number of micro increases much faster than the number of macrostates. But for ordered systems such as everything heads, there's only one, whether I have 1 coin, 2 coins, 3 coins, 4 coins, 5 coins, 100 coins, or a number equal to Avogadro. So 6 times 10 to the 23. Number of coins only has one microstate corresponding to that macrostate of everything face up. So what is the chance actually of finding that in an almost infinite number of probabilities, of microstates? It's going to be 1 over an infinite number of microstates. And so what's the probability of 1 divided by infinite? It's 0. So what is the probability actually of finding that state? Almost 0. So what do we say is that because systems disorder have higher probability, if this is really random, I do expect that if I actually have a large number of particles, which is a large number of particles, I'm going to be finding results corresponding to those systems with a higher probability. This is exactly what entropy is telling you. Entropy is increasing because it's going final entropy minus initial entropy. These systems are ordered, and so they have an entropy that it's smaller than the final entropy. This is the arrow of time that sometimes we hear, right? Entropy is the arrow of time. Why? Because the particles are the systems, the disordered systems are much more likely to happen than ordered systems. So when you say why systems tend towards disorder, it is because statistically there's many more ways in which you can organize the same macrostate at that disorder. There's more microstates that correspond to that disordered macrostate. The number of microstates that correspond to an ordered macrostate. And so that's why probabilistically we can understand that entropy is just telling and things tends to disorder, because by statistical reasoning we observe that indeed it's much more likely to find one than another. And this is the statistical understanding of entropy. And there is another subtlety, let's erase here before we go. Let's make sure that this is the question. Yeah, anyway, this is all the entropy. This is just solves the problem. But let's one last subtlety that we want to say with respect to this entropy now that we have the microscopic. I think, again, from the microscopic, you see everything we started. Temperature is macroscopic, and then we introduce the micro, which is the kinetic average energy of the particles. Then we have heat, which was macroscopic, specific heat, latent heat, fusion, and increasing temperatures, and then we have the micro. And now we come up with entropy, which we observe from the point of view of engines. Remember Kelvin's statement, there is no free work. If you have work, you have to pay a discharge of cold heat. There's no way around that, second law of thermodynamics. But then there's also Clausius saying, excuse me, the change of entropy is always positive. When you define the change of a system's entropy, entropy being a property of the system in equilibrium, I observe that the entropy always increases. It is equivalent to what Kelvin is saying, but now he even offers a mathematical description, right? Because Clausius is telling you that the change in entropy is equal to Q over T, right? And this is telling you this is always larger than 0. Now it's telling you why heat flows from hot to cold, as we just saw in the previous example. So we have entropy understood as there is no free work. If you want to have work, there's no ideal systems, which is what Carnot was telling you. Ideal systems are going to be anyways lower than 100%, and then Kelvin is going to tell you this is because there's a fundamental law that says that you can never get all the heat into work. When you have heat and work in an isolated system, there needs to be, or a system cannot just produce all heat into work, right? The sole production of heat cannot go into work. Some of it needs to be discharged into the cold thing. That was Kelvin. Then we have Clausius telling you this, and now we have Boltzmann with his statistical understanding. We can understand why things flow the way, why heat flows from hot to cold, because hotter systems are, because if you calculate an amount of disorder, is much more likely, basically, it's statistically. So we say entropy is disorder. Well, yeah, but then why does entropy tend to more disorder? Because it's much more likely. Let's see one last idea in here. Let's erase here one last idea of entropy to finish this chapter. One last idea we want to discuss is this idea of entropy increasing disorder and then available energy. So let's say that we have a system of particles, and I just tell you, let's say the particles are just some gas, and they're just moving randomly. This one is moving here, this one is moving here, and this one is moving here. What is that? What I consider useful energy. Useful energy is that I can actually use as work, because we're always working from the point of view, we're always thinking from the point of view of work. We're always trying to think, what can I get out of this? Where this is selfish. So basically, let's say that we have some particles and they're just moving, each one with a different velocity in a certain direction. Okay, these are the particles, right? And they're just moving randomly. And so which system is much more organized or ordered? This system, or a system with all the particles, let's say, are going in this direction. Which one is more ordered? Well, it seems to be this one more ordered, because every one of the particles, which is this one, has the same velocity. So there's only one way in which, let's say, I can organize all the particles to be like this. Whereas if I calculate the average velocity, so if I add velocity of this particle, velocity of this particle, velocity of this particle, so if I calculate the average velocity of all the particles here, which is the sum of all the vectors then divided by 5, let's say, which because it's 5 particles, there's many more ways in which I can find the same velocity average for this system that I can find this one. There's only one way I can find this velocity, which is when everyone is pointing in that direction, right? And so there's this is much less likely than this one. But why is that important? Because what happens if all the particles are moving towards there? What I expect is that if I take from the macro perspective, each one of those, let's look at it from the point of view of this wall. If I take that system and I see this wall, maybe one particle is just slightly hitting that wall. So you have to project and say, okay, this particle is hitting the wall. So what is the force that wall experiences, or force done in that work? That wall is going to be given just by a single particle. And so I say, okay, this force is little, and then I just say, let's say it produces certain displacement, okay, of the wall. What about this scenario here? Well, I'm going to have more particles now hitting the wall because all of them are targeting the wall. So I'm going to have a larger force producing a displacement. So what is this? This is work. And what is this? This is work. But in this scenario, work here is larger than this one because all of them are aligned in the direction of displacement. What I expect to find if I have this object where everything is moving randomly, with particles moving in every direction, a time later, what I expect to find is exactly the same thing, but maybe now the particles are moving in a different direction. There is no net movement of the particles. Whereas if the particles are aligned, what I observe a time later is that the particles were moving like this, and now the particles keep moving that way, and the object as a whole has moved, has translated. So now there is a displacement with a force acting in the direction of the displacement. There is a work in here. So I can extract work because to do work I need to apply a force aligned with the displacement. So I need to have order. The particles need to be ordered in that direction if you want to think of it that way. So then I can see that what happens when I increase entropy is that I lose the possibility. I'm going from this system to that system. I'm losing the possibility of extracting work. The number of molecules now aligned in the displacement of the in the direction of the displacement is smaller. So I have less available energy to actually perform work. The universe is tending, because the universe is a system that contains everything. The universe as such is isolated. There is no external interference. Therefore, second law of thermodynamics is telling you for the universe, universe understood not like anyways, universe, right? It's always increasing. And so everything is tending to a larger disorder. Why? Because it's much more probable. Disordered systems are much more probable than disordered ones. But as systems get disordered, then the possibility of extracting work from those is much smaller, because the forces are not anymore acting in the direction of the displacement, which is the requirement from mechanical understanding of energy. Energy is capacity of doing work. Work is applying a force over displacement. To apply the force over displacement, these are vectors. These need to be aligned. In this case, all of them are aligned, but in this case, each one is pointing in every direction. So I have less molecules aligned, or less amount of energy actually, or the force aligned into the direction of displacement. So I can extract work from these systems, but I cannot extract work from these systems. So this is basically the idea here of why entropy is telling you also is related to the amount of energy. And then we go back to that example that we're saying. There's a dam with water, you open the dam and the water falls and moves the turbine and get work. Once the dam goes to the bottom of the river, the water falls, then you cannot extract any more work from that water. So the idea is you want to do it with efficiency, because the entropy is going to increase, and once it increases, you cannot extract more work. So it just turns out that you extract work here, but in an efficient manner. You're not extracting all the work that you could have extracted, but you have transitioned, let's say, to a system with higher disorder, second law, and so you're going to have every time less and less and less work available to be extracted. Just another way of saying that, if you wish, but these are the three understandings of the second law of thermodynamics: arrow of time, efficiency of heat engines, but also why heat flows from hot to cold. All of these things together gives us this idea of entropy. Entropy is not just simply disorder, like, oh, is disorder is chaos. It makes sense now to us, and we have closed that gap and answered that last question. What is hotness? How hotness happens? Why heat flows from hot to cold? We have closed then thermodynamics and the physics of heat chapter.